So in chapter 7, we're going to talk about power series, and we're going to see exactly how useful these are in complex analysis. But before we do that, what I want to do is chapter 7 is basically all a reminder of all the stuff that you've seen so far, maybe in Calc 2, Calc 3, about power series. There's in section 7.3, we'll talk about a slightly new idea. If you've taken a real analysis course, you've seen this. It's going to be talking about functions that are sequences themselves. So sequences of functions, but we'll talk about that at the time. So for now, I just want to remind you about a bunch of things related to series and sequences. A sequence is basically just a function, and we're talking about specifically complex valued sequences. And we'll have to use what we know about real valued sequences, but yeah, we'll see how all this fits together. But a sequence is just a function, f, going from some set e to the complex numbers, where e is a subset of, say, the positive integers or sometimes the non-negative integers. And it can be really any subset that we want. It can be a finite subset. It can start at 1. It can start at 4. It can start at 70. It doesn't matter. And so typically, instead of thinking about, let's say we have a function f that starts at, say, the positive integers. So it goes from 1 to infinity, and then it maps to the complex numbers. You could have, instead of saying f of 1, typically what you do is you write that as a sub 1, and f of 2 is a sub 2, and so on. Okay, and so whatever the sequence is, maybe the sequence is f of n is e to the, maybe e to the pi in or something like that. I don't know, e to the, let's just say in. Okay, and so if this is your sequence f of n, then your a sub n is exactly e to the in, right? And you can go from there. So that's a sequence. It's just a function whose domain is a subset of the non-negative integers. Okay, so that's a sequence. And again, I think it's useful to talk about some examples here. Okay, so for example, if we were to have a sub n is I to the n over n factorial, where n is greater than or equal to 0. Okay, this would be a good example of a sequence. Then a0 would be, let's see, I to the 0 over 0 factorial. And so that would be 1 over 1. So we'd have 1 over 1, which is 1. A1 would be I over 1, so just I. A2 is I squared over 2 factorial, so that's negative 1/2. A3 would be negative I, so I cubed over 3 factorial. A4 would be I to the 4th over 4 factorial, and so on. Okay, so this could be your sequence. Okay, we typically write, so there's a few ways to write the sequence. We're typically going to write the sequence a sub n. So if we have a1, a2, a3, I use parentheses here because parentheses emphasize that we care about the order. So this is a function, and therefore the order is going to matter. So what I mean by that is that if you were to switch the first two values, you would have a different function, right? If f of 2 and f of 1 switched, then there would be a different function. And so here the order really is going to matter. And we care about the sequence here, a1, a2, a3. And so we typically write that as the set, or as the sequence a sub I, as I goes from 1 to infinity. Okay, or sometimes if the index is clear where it starts and stops, we'll write that as just a sub I. Sometimes we write it as a sub I where I is greater than or equal to 1. Okay, these are all just kind of analogous ways of writing a sequence. So we're going to say that a sequence a sub n or a sub I converges to L if for all epsilon, okay, so if for all epsilon there exists an n so that a sub n minus L is less than epsilon whenever little n is greater than or equal to big N. This is very similar to the definition that we went through in chapter 3 when we were talking about functions that go to infinity and the Riemann sphere and all that. Okay, so these are basically the same, because a sequence is basically just a function with a restricted domain. The domain's just the set of, maybe the set of non-negative integers or some subset. Okay, so the definitions will be the same because it's really the same object. And so that's what it means for a sequence to converge to a value L. Okay.